In this video, we'll talk about finding derivatives of the other inverse trigonometric functions. So all the other trigonometric functions and their inverses can be done in the same way. Let's go ahead and work through them real quick. So I want to find the derivative of y equals inverse tangent of x. How can I do that? Well, let's move the tangent to the other side by applying tangent to both sides. I get tangent of y equals x. I can then differentiate. Tangent, derivative of tangent is secant squared. Secant squared of y dy dx equals 1. So dy dx equals 1 over secant squared of y. To convert this, I'm going to use a triangle again. So y is again my angle. And now my tangent of y is x. So tangent is opposite over adjacent. That gets me x. My hypotenuse is then square root 1 plus x squared. Secant of y is then hypotenuse over adjacent, which is just root 1 plus x squared. Then I put that in for secant squared, I get 1 over 1 plus x squared. That there's the derivative of the inverse tangent function. It's 1 over 1 plus x squared. We can do the same for secant. So in this case, secant of y equals x. Apply a derivative. Derivative of secant is secant tangent, so I get secant of y tangent of y times dy dx equals 1. So dy dx is 1 over secant of y tangent of y. And again, we always use a triangle to convert this back to x's. Let's build the triangle. Again, y is our angle. And secant of y is x, which is hypotenuse over adjacent. So x over 1. So the opposite side is root x squared minus 1. And so we then see here that secant of y is obviously x, because that's what it was when we defined it. And tangent is opposite over adjacent is this root x squared minus 1 term. And so we get that this should be 1 over x root x squared minus 1. However, this here only works if x is a positive number, because I need the setup here to be positive. Because x is a length, it's got to be positive. If x is negative, I have to play with some signs. And so it turns out what you get at the end of that is if x is negative, I need to put negatives on all this, because this derivative here should always be positive just based on the graph of the function. So our end result we get from that is this is not quite right. I need an absolute value sign on this x to make sure this whole expression here is always positive. So what I really get is that the derivative of secant inverse of x is 1 over absolute value of x, root x squared minus 1. That one's a little trickier, hard to remember, but that's what you get for this derivative here for this function. Now for the other three, you could work them out the same way for cosine, for cotangent, and for cosecant. However, based on how triangles work, there's some nice identities we can use to make this easier. And those identities are the following. They're basically complementary angle identities, and they work like this. Why does this make sense for a triangle? Well, if I draw out a triangle here, now for this setup here, x refers to ratios of side lengths. So for the cosine, for instance, if I have an angle theta here, the fact that theta is this angle up here means that cosine inverse of x is theta, means cosine of theta equals x. Cosine of theta means that then x over 1 like this. But what does that mean? Well, if I take this other angle over here, then sine of phi also equals x. And based on right triangles, we know that theta plus phi equals pi over 2. And so that's where all these formulas come from, by realizing that if I take the other angle, its cotangent is the same as the first one's tangent, and back and forth to give me those identities. Now, what this means in terms of differentiation is that the derivative of inverse cosine should be negative the derivative of inverse sine. And the same for the other two as well, for cotangent and tangent, and then cosecant and secant. So as an example, right, the derivative of inverse cosine of x should be negative 1 over root 1 minus x squared. And same for that two as well. So that's the idea of how we can use the same techniques and the same triangle pictures to figure out the derivatives of the other inverse trig functions, not just the sine function, And now with these, you can go and solve a bunch of derivatives with chain rules and projects and all that stuff that involve these inverse trig derivatives.